Today we'll discuss about the inverted V antenna, which is often the first antenna which a radio amateur builds himself. It is quite simple to build. I had also built one long back when I started coming on air using my homebrew equipment. See how it is built. The inverted V dipole antenna needs only a single mast. That's the advantage. While a horizontal dipole antenna will require two masts, this requires only a single mast. Here we have mentioned that a non-conducting mast has to be used. If you are using a conducting mast, then the mast should be grounded well. Then you need two other small supports. This will be a little away from the ground, and insulators are needed. There are insulators here from the mast, and this is the connection of the coaxial cable, one to either side of the antenna limbs. These two are copper wires, made of copper wire, thick gauge copper wire. It can be insulated copper wire or non-insulated, no problem. And it could be single-stranded or double-stranded or multiple-stranded copper wire, no problem about that. And what you have to use is the coaxial cable. If you are using a coaxial cable, you will need a balun over here, because antenna, the inverted V dipole antenna is a balanced antenna. So coax is an unbalanced line. So you'll have to put a balun over here before connecting the antenna. Then the insulators we have already mentioned. The inverted V antenna has an advantage that it has a low angle of radiation. Low angle of radiation means it will go to the ionosphere very well. And when it goes to the ionosphere very well, it can be reflected down to the earth to a longer distance. So inverted V antenna is supposed to be better for long distance propagation. That's another reason why amateurs go for that. Those who cannot build a large beam antenna. And when you have a low angle of radiation and better DX work, this is one of the best suited. Then regarding the directivity, usually the horizontal dipole, if it is a horizontal dipole like this, it will the beam will go in both directions towards the one side and opposite side also. Towards the end of the antenna, there will be hardly any radiation. In case of inverted V, since it is angulated, it is not as directive as the horizontal dipole. There is some radiation in other direction because this is at an angulation. So it is partly an omnidirectional antenna. Though it is not fully omnidirectional like a vertical dipole, this has some omnidirectional property that also helps in working DX in different directions. If it is a horizontal dipole, it can go in these two directions only. Towards the end, there will be no radiation. But inverted V dipole, there will be some radiation all around. So it is useful for a radio amateur who does not have a facility for a beam antenna with an antenna rotator. You know, beam antennas are costly, difficult to build. Rotators are very costly. So all those things are not there for a beginner. So when a beginner uses a inverted V, these are advantages. But some care is needed. For example, these two are very near the ground. Suppose somebody is going to test this antenna, it could give a RF burn, especially when the power is high. So you would like to have some protection here. That is at least, suppose you are installing this mast in the garden and this end is in your compound itself. You should see to it that nobody will go and test these ends. These are some precautions which you will have to take for protection of your own people and yourself when you are using an inverted V antenna. In case of horizontal antenna, dipole antenna, this is not required because both ends are quite high and nobody is going to touch it. So this is the difference between inverted V antenna and a dipole antenna. Thank you very much. Zigzag mounting of the inverted V 40-meter antenna has been done just because I do not have space here for a regular mounting. Central pole is a 3-meter length of CPVC, chlorinated polyvinyl chloride, hot water pipe tied to the fencing of first floor terrace. Height of the antenna top will be about 6 meters from the ground. There is an iron frame for the terrace fence about 2 feet below the top of the mast, which could have some effect on the properties of the antenna. One limb of the inverted V goes straight down and the lower end is about 2 meters from the ground, tied to a metallic pole with a nylon string. Spacing from the metallic frame of the compound fence will be about 1 foot. Other limb goes down in one direction first and then in another direction, both being tied to the metallic frame of the fence using nylon string. Coconut trees seen in the picture are actually in a compound across the road and not anywhere near the antenna, though it appears like that in the oblique view. If they were, I could have tied my antenna high up easily, as I used to do at my parents' home about 4 decades back. I had bought 30 meters of RG213 coaxial cable with PL259 connectors pre-crimped on either side for convenience, as I am not good at crimping PL259 connectors. Actually, I do not need 30 meters, but that was the only length with pre-crimped connectors available at the dealer. There are about 23 turns of surplus RG213 coaxial cable with a turn diameter of about 20 cm kept inside the shack. I wonder whether it will act as a line isolator or choke off all the RF output of my radio. In the former case, it will be beneficial, while in the latter case, it will reduce the effectiveness of my amateur radio communication. I have not calculated the inductance of this coil and I am not sure about its effect on the antenna system for an inverted V zigzag antenna. Though I have SNEC Pro 7 antenna modeling software installed in my laptop, I am yet to learn how to use it. Initially, when I tested the SWR of the antenna, it came as around 10:1 with the high SWR warning light coming up in the radio. Immediately I brought down the antenna and checked the junction box. To my dismay, I found that the soldered joint of the central conductor on SO239 had given way, possibly because the solder which I had used was pretty old and I did not have soldering flux. That was why I immediately bought my new soldering kit by same day online delivery, which I got for 250 INR, around $3. Resoldered the joint as best as possible and remounted the antenna for further testing. Of course, I had to use my old 65-watt soldering iron, as the one in the kit was low power and not suitable for soldering SO239 connector. Initial SWR on remounting was around 3:1 at the lower end of the 40-meter band and around 5:1 at the upper end. I had put extra wire length as a loop at both ends for attaching nylon wires. First, I trimmed off about 26 cm of those from either ends, and the SWR came down to 2.5:1 on the lower end of the band and 3:1 at the upper end. Next, I removed another 10 cm from both ends and got SWR to 2.25:1 at lower end and 3:1 at upper end. Removing one more set of 10 cm each brought it down to 1.6:1 near the lower end of the band and 2.5:1 at the upper end of the band. Here you can see the pieces of wires spliced off in the tuning process. At this level, I checked SWR on 21 MHz band as well, the third harmonic of 7 MHz on which a 40-meter antenna can resonate. It was 1.8:1 at the lower end of the amateur band and 2.71:1 at the upper end. Though there is a built-in SWR meter and a limited automatic antenna tuner facility in my radio, I am using my cross needle SWR meter for checking the testing phase, as I am more familiar with it. I have used a short length of HLF 200 cable, which is supposed to be an LMR 200 clone, for connecting the SWR meter to the radio. Patch cable has PL259 connectors at both ends. One end is connected to the radio and the other end to the SWR meter. End of the RG213 coax inside the shack is connected to the SWR meter for testing. Change the orientation of the zigzag limb of the inverted V to avoid some interference to the courtyard and tested once again. This time I was happy to get SWR of 1.2:1 at the lower end of the band and 2:1 at the upper end of the 40 meter band. I could hear net control of Chamina net loud and clear.
Thanks, Unni, for checking in 59 plus 15 dB. Who is the contact?
Most other stations were also coming in very well. Finally, I could also check in to the net with this very compromised mounting of a half-wave dipole antenna. I know that my work is not over. Making the connections and mounting secure is another job. Rechecked on 21 MHz as well, and the SWR was unchanged at the lower end of the band at 1.8:1, while it had come down from 2.7:1 to 2.25:1 at the upper end of the band. I am yet to try that band for RX and TX, as I am not familiar with band opening times. I have to continue my efforts to bring down the SWR more on higher part of both bands so that I can drive full 100 watts from the radio. Still, I will not reach the legal maximum of 400 watts for my class of license because I do not have a linear amplifier, nor do I intend to purchase one. There is a high elevation pass of International Space Station in this region, and I have tuned to the uplink and downlink frequencies as shown on the Argentinian AMSAT web page. And the squelch has been kept open, that is the hissing noise you are hearing. R tone has been set. You can see R tone has been set at 67. I was just counter checking that. I knew I had already set it. Then you can see that the frequency is above the nominal frequency. Nominal frequency is 437.800. But the uplink I have programmed only at the nominal, because now due to technical reasons I am using my 40-10 meter combination dipole antenna, so I will not be able to get through to International Space Station at very low elevations. Now you can see that the needle color change has occurred. The green bar is the elevation. Elevation and azimuth are also displayed there, and you can see the Doppler changes in frequency which you have to make while manual tuning. The altitude is shown here as 413 km, distance as 1900 km, and you can see that azimuth needle is gradually moving, as well as there are changes in Doppler frequency which is going to occur gradually. In uplink, the frequency is given as 145.986, but I have kept it 990 because when satellite is at low elevation, I am sure I will not be able to transmit and reach the satellite with a antenna which is for a totally different band, not even for VHF or UHF. but HF antenna I am using. It's an experimental setup. I've been able to contact space station once or twice using this setup earlier, but that's mere luck. Not always it is possible. This time it is a high elevation pass, so I am hopeful at least of hearing some stations. Today morning I could hear 3 stations during a 45-degree elevation pass, but I could not reach the space station with my signals, even though I tried calling 3 times. Now the satellite is at 15-degree elevation and Doppler frequency up. Downlink is slightly lower now. Instead of 810, it is 809. I will make a change only when it is 50% of the step. The step in my radio is 5 kHz. So when there is 2.5 kHz difference, I will make a change. When the satellite's signal is acquired by my radio, the open squelch is likely to close. That is how we know signal is being acquired. You can see change in the hissing sound. That means some signal from the satellite is being acquired. Elevation is 28 degrees and distance of satellite is only 700 km, much nearer now because the elevation has increased. You can see that the uplink, some signal is coming. Uplink has come to 145.987. So we are hearing somebody. But I went down by 1 step. VU to Juliet Oscar. Mike Zulu Tango, Yankee Foxtrot Delta, VU to Juliet Oscar 5 and 9. I think VU to Mike Zulu Tango and Yankee Foxtrot Delta have heard me. V2 Alpha Alpha Papa, V2 JO 5 and 9. I am coming down 1 more step. So this time I think 3 stations have heard me. Mike Zulu, VU to Mike Zulu Tango, VU3 Yankee Foxtrot Delta and VU2 Alpha Alpha Papa have heard me. Now the downlink beyond the time of closest approach, the elevation is coming down, now 47. I have reduced 1 more step in the downlink frequency. I'll stop recording now because I don't think I'll get more signals.